The human skin, our largest and most visibly aging organ, has long been a canvas of time. Wrinkles, spots, thinning, and dryness are the most familiar signs, but beneath these surface changes lies a cellular mosaic of aging processes that are anything but uniform. Far from being a flat sheet of tissue, the skin is a complex, layered ecosystem of fibroblasts, keratinocytes, melanocytes, immune cells, and vasculature, each population aging at its own pace, in its own way. Senescent cells, once thought to be mere debris in the aging landscape, are now emerging as active players in this drama. Some are destructive, some are protective, and some are just along for the ride. The challenge and the opportunity is to figure out which are which, cell by cell, face by face. Enter artificial intelligence and high-resolution imaging technologies, a new alliance of computation and biology that promises to change how we understand and treat skin aging. With advances in multiphoton microscopy, optical coherence tomography, and transcriptomic profiling of skin biopsies, researchers can now observe not just the external features of aging, but the underlying cellular dynamics, where senescent cells are accumulating, how they're behaving, and what signals they're broadcasting. And AI, particularly machine learning models trained on this flood of data, is helping to make sense of it all. It can cluster cells into functional subtypes, predict SESB patterns, and link certain cellular behaviors to visible skin aging traits like loss of elasticity, dullness, or hyperpigmentation. What's emerging is the realization that senescence in the skin isn't monolithic. It's not just more senescent cells equals older-looking skin. Different senescent subtypes have different effects. Some secrete high levels of matrix-degrading enzymes that break down collagen, leading to sagging and wrinkles. Others are propigmentary, contributing to uneven tone or age spots. Still others may be immunosuppressive, dampening the skin's ability to respond to injury or infection. And then there are senescent cells that actually serve useful functions, like limiting fibrosis or promoting controlled inflammation after damage. The upshot? Two people with the same chronological age and similar sun exposure might have very different senescence profiles and therefore very different responses to the same anti-aging treatment. This is where personalized skin therapies begin to make sense, not as a luxury but as a biological necessity. With AI-driven senescence mapping, it's now possible to imagine anti-aging regimens designed not around skin type or age group, but around dominant senescent cell phenotypes. A person with high MMP-secreting senescent fibroblasts might benefit from topical xenomorphics that inhibit protease activity, preserving extracellular matrix integrity. Another individual with pigment-producing senescent melanocytes could receive customized tyrosinase modulators or laser treatments guided by spatial data on melanocyte clustering. Someone with extensive immunosenescent keratinocytes might be better suited to immune-rejuvenating peptides or low-dose senolytics that enhance turnover without compromising barrier function. This shift also changes how we think about diagnostics. Imagine visiting a dermatologist and getting a non-invasive imaging scan that creates a high-definition senescence map of your facial or hand skin. The readout could indicate regions with pro-inflammatory SESB dominance, zones with barrier dysfunction, or pockets of regenerative resistance. From this, a tailored protocol could be generated, combining ingredients like retinoids, antioxidants, senolytics, growth factors, or even gene-editing actives, not based on trends or generic advice, but on the specific needs of your skin at a cellular level. One person's miracle cream could be another's mild irritant, not because of marketing hype, but because the biology underneath is just that different. What's especially promising is that some of these tools are already being used in research and high-end clinics. Skin organoids and ex vivo skin slices, when paired with AI analysis, are helping scientists understand how different senescence interventions play out in complex tissue systems. Companies are beginning to test how various compounds affect specific senescent subtypes. Some quiet the SASB, others gently reprogram the cells, and some remove them altogether. The dream is a future where topical products don't just promise anti-aging, but are formulated to reduce the exact subtype of cellular dysfunction driving your particular signs of aging. And while some might see this as yet another frontier in cosmetic overengineering, the implications go deeper. Senescent skin cells are linked to wound healing delays, inflammatory conditions like eczema and psoriasis, and even skin cancer risk. So this isn't just about vanity, it's about function, protection, and resilience. Personalized senescence modulating therapies could improve quality of life, especially in older adults whose skin has become more vulnerable to injury and infection. Aging skin isn't just about looking older. It's about staying intact, staying functional, and staying connected to the world around us. In the end, mapping the skin's senescence landscape isn't about finding one perfect anti-aging solution. It's about embracing the complexity of aging and designing smarter, more humane interventions, ones that recognize not all zombies need to be eliminated, and not all aging is bad. By using AI to understand which cells are helping and which are hurting, we're not just treating the symptoms of time, we're negotiating with it, cell by cell, wrinkle by wrinkle.